give you this summary sheet so that you guys can have this as reference. I grouped it into first 2 pages is fall semester review. 3rd and 4th page is the spring semester review. And also some students have asked about, can I get a review for all the theorems that we covered in the first semester? So I've given this to you in the past, but I wanted to give this out to you again as well. Kind of a summary of extreme value theorem, a summary of mean value theorem, summary of Rolle's theorem, first derivative test, test for concavity, second derivative test. Okay, we'll spend a day on limits next week, continuity conditions, and then intermediate value theorem. Okay, so just for your reference, some students have been asking about a summary sheet for all the topics that we've covered so far, but we'll definitely go back and look at these individual topics in more detail over the course of next week, and also when we come back from spring break. Okay, any questions right now? Yes.
How many FRQs are there?
Oh, it'll just be one FRQ. So if you look at the morning review, yes, good question. Morning review. So I'll probably give you, I'll give you a graph. I'll give you a graph. I'll give you a table. I may give you a function, and I'm just going to be asking a bunch of questions from this. So it's just based off of the same stem, and then just a bunch of questions. You can, so it's just basically one extended FRQ. That's it tomorrow. Okay, but today we're going to go through page 15 through 18. So go to page 15. Okay, so it says f and f prime are differentiable functions. So all that means is that we're dealing with smooth curve here. It's important. It's good for us to know that because we have very limited information from the graph, right? We don't know, there's a hole or asymptotes because we can't see it. But here it's kind of provides that reassurance that it's a smooth curve all the way through. Values of f and f prime are given as select values of x in the table. So for part A, if g of x equals f of x quantity squared, find the instantaneous rate of change of g at x equals 9. This is just another way of saying find g prime of 9. But before we can find g prime of 9, we have to first find what? Yeah, let's find the derivative function, right? So it's always going to be a two-step process. We always have to find the derivative before we can plug anything in. So let me rewrite the function to help us see the process that's involved here. So look at how this function is built here. If I want to find the derivative, what's involved? You guys see it? Okay. Power rule, okay, but something else I want you to say. Good, there's a function within a function. Do you see it? There's a bracket, which is its own function, and there's the f of x, which is its own function. So we got to go through chain rule here. So chain rule says outsize derivative times insize derivative. Okay, so the outside is the bracket squared, and the inside is the f of x. So we're taking terms with each of their derivatives and building it out. So what's the derivative of bracket squared? Just 2 bracket, right? It's like x squared. X squared is just 2x. We're just treating that bracket as its own variable. So 2, and then we leave the inside alone. Now that we're done with the outside derivative, inside derivative, f of x becomes, what's the derivative of f? F prime, yeah. So the outside is power rule, but the inside is function notation. Okay, replace. Now you can replace every x with 9. We look to our table here. F of 9 is -2. F prime of 9 is -4. All right, any questions with first part there? Okay, part C, k of x is equal to f of 3 of x times x squared plus 1. Find the slope of the line tangent to the graph of k of x at x equals 3. What is this asking for us to find? Okay, find the slope of the tangent line. So find k prime of 3. Okay, so notice that it's asking for both A and C are asking for the same thing, just worded differently. So instantaneous rate of change, slope of the tangent line, they all refer to find the slope, find the derivative at a point. All right, so before we find k prime of 3, we first have to find k prime of x. To find k prime of x, look at how this function is given to us. Okay. What's involved here if we want to find the derivative? Product rule. Notice that these are two functions that are outside of each other. There's some multiplication separating them. Good. So product rule. And there's something else that I want you to say. Something about that f of 3 of x. There's also a little bit of what going on there. Function within the function. So chain rule, yeah, a little bit of chain rule there. Outside derivative times inside derivative that has to occur within that f of x. Okay, so now let's build our derivative. Okay, so what's the derivative of f of 3x? Okay, outside derivative times inside derivative, right? There's a function within the function. What's the outside derivative? F prime of 3x. Yep, we leave the 3x alone because we're not ready for it yet. We're just going to copy that down. That's the outside derivative. And then times, what's the inside derivative? Times 3. The original g function. Right, so now it gets a lot easier. Now you're just replacing every x with 3 and then cleaning up and then pulling from your table. Okay, see if you can finish that. All right, any questions there? Okay, look at part D here. Find the depth integral from 0 to 3 of f double prime of 3x. We know that we got to take the antiderivative. We know f double prime is going to rise up to f prime, but there's something that we need to take care of. We got to go through a little bit of what? Yeah, use substitution, right? Got to take care of that 3x. We know that there's going to be a coefficient left over out of that. Okay, we know there's a 1/3 that's going to be left over in front. Okay, we know the 1/3 is going to tag on to our antiderivative, but we know that f double prime is going to rise up to f prime. Right? We know derivative is going to keep making our way down the derivative, but with antiderivative, we're going to kind of go up that chain. So we know f double prime becomes f prime. The 1/3 tags along with it. Okay, so there's the antiderivative. The integral notation in du drops out because we took care of the antiderivative. And now we have to involve the bound somehow. Can I plug 0 and 3 directly into this, into the u? Okay, what's the issue right now? Yeah, we got to match the variables, right? Either we convert the 3 and 0 in terms of u, or we bring the u back in terms of x, and then we can use the original bounds. Okay, but right now there's a mismatch. So I think the one that students prefer is bring the x back, and then use the original bounds. Okay, upper bound first. And now you can pull from your table. Look at the table to find f prime of 9. Look at the table to find f prime of 0. Right, so f prime of 9, f prime of 0. Okay, page 16 when you're ready. Everybody good on this page? Okay. Okay, f and f prime are differentiable functions. Value. Okay, so same direction, same table. Let n of x be given as the definite integral from 0 to x squared of f prime of x dx. Let me change this a bit because technically this upper bound should not be the same variable as this, so this should really be f prime of t dt. F prime of t dt. But essentially it's the same. It's still f of x. We just want to make sure that if there's upper bound variable that it's not conflicting with the variable that we see there. So it says evaluate n of 3. So define n of 3, I'm just going to replace every x with 3. Okay, the upper bound gets replaced with 3 squared, which is 9. So this is applying first theorem here. We know if we take the antiderivative of f prime, it's going to rise up to f of x, and then we can plug in the upper and lower bound. So first fundamental theorem of calculus, the integral from a to b of f prime is going to be f of b minus f of a. Okay, so f prime rises up to f of x, and then we can plug in our upper and lower bound. Okay, something doesn't make sense, or you want me to clarify something, just go ahead and ask. I want to make sure that you feel comfortable with every step that we're taking here. Okay, go to your table of values, f of 9, and f of 0. Okay, next up, find n prime of 3. But before we find n prime of 3, we're going to find n prime of x. Okay, but to find n prime of x, there's a little bit of procedure we have to go through, so let's talk about that. So to find n prime, I need to find the derivative of this mess on the right side here. Let me just write out what I want to do. I want to find the derivative of this expression. Now, that's referring to second theorem. Okay, so this is on your formula sheet here. Second theorem says, if I want to find the derivative of a definite integral, we know that these two operations will cancel each other out because these are opposite operations. But the only thing that's left is that upper bound gets inserted into the expression that you see there. But there's also something else. There's also times p prime. We still have to multiply by the upper bound's derivative. Now before, we didn't have to do that because if the upper bound was just x, x would just become 1 and nothing additional would have to be, would change the answer. But anytime it's anything different than an x, that p prime is going to produce something other than 1. So we know these two cancel out. This x squared gets inserted in for t. So f prime of x squared times what? 2x. Okay, now we can replace x's with 3's to find n prime of 3. Okay, find f prime of 9 from your table. Okay, part J. Let q of x equal to natural log of f of x. Find q prime of x. Sorry, find q prime of 5. Before we can find q prime of 5, we're going to find the derivative. So here, there's a little bit of chain rule here. There's a outside and inside function. We got to take natural log's derivative, and then we can involve the inside. So a little bit of chain rule here. Okay, so first up is this natural log of u. Okay, so as a reminder, this is on your formula sheet as well. Natural log of u's derivative is u prime over u. What's the u value in this natural log function? Okay, the u value is that f of x, right? It lines up nicely with the rule that we want to apply. So what's u prime then? Just f prime, right? Okay. Over u, which is f of x. Okay, replace every x with 5 and then use the table. Yeah, anytime we involve u prime within a derivative rule, that's basically like a baby chain rule occurring. Okay. Okay, part K is also, notice that there's also a little bit of chain rule here, right? There's a function within a function, so we first have to find r prime of x. Let me identify here. There's an outside and inside portion, right? Here, the outside portion is the f parentheses, and the inside portion is that natural log of x. Okay, so outside's derivative, f becomes what? What's f's derivative? Just what? F prime, yep. And then we keep the inside intact times natural log's derivative. So natural log's derivative is u prime over u, so 1 over x. Now we can plug in. Replace every x with 1. Okay, what's natural log of 1? Just 0, yeah. F prime is 0 from your table. I want to do page 19 before we do a little bit of the homework. So page 19, okay, everybody good so far with this page? So page 19 says, this is FRQ variations for finding values of function graph given the derivative graph. So there's been just some questions about, well, how do I know when I have to involve adding an initial position plus displacement if I want to find a final position versus when can I just use the integral given to me? So I want to kind of show two different variations so that you can kind of see that distinction when we're trying to find a value using a derivative graph. So this is the figure of f prime, which is the derivative, which is differentiable function. The areas are given in these 3 regions here. We got region 1, region 2, region 3, and the areas are 7, 6, and 8. Now they give us the areas, but we know the definite integral are going to be positive or negative depending on whether it's above or below the x-axis. So this first region here is above the x-axis, so that's going to correspond with 7. The second is an area of 6, but it's below the x-axis, so we'll call this negative 6. And the third region, they're saying it's an area of 8, but we know definite integral accumulation of negative y values will give us negatives. So it says find f of -3 given f of -2. Well, I know that if I take the integral of a certain region, it'll give me the displacement. It'll give me the net change. But if I want to find where the physical location is, I have to tack it on to my starting point. So I need to rely on this formula here, which says that any location I'm looking for is going to be a given or starting or initial position plus displacement. So if I want to find f of -3, it's going to follow this formula. Your initial position is whatever is given to you. Here, what's given to you is the fact that f of negative 2 is 4. So we're going to start at f of negative 2. And if I want to find f of negative 3, if I'm starting at f of negative 2, I need to bridge that gap between those two locations. So to bridge that gap, I'm going to take the definite integral plus. Now, when you do definite integral, make sure that you always match your lower bound with your a and your upper bound with your b. You're starting here and you're ending here. Initially, the bounds may be out of order, but if they are, we'll take care of that later. But initially, you have to make sure you follow the rules and say that, okay, if I'm starting here, that means that's my lower bound, and I'm ending with my upper bound. Now we can take a step back and say, okay, I want to read the graph preferably from left to right so that I'm not having to change the signs as I'm looking at all these numbers. So what do you notice here? Yeah, let's flip the bounds so that we can easily read the graph from left to right. So as I flip the bounds, now I can change the sign to make that adjustment. So my plus becomes a minus, and then my bounds goes from negative 3 to negative 2. Okay, f of negative 2 is 4 minus. And now the definite integral from negative 3 to negative 2 is this region 7. But I'm just going to read it with what's given to me, and then I already adjusted for that sign change. So 4 minus 7. Okay, see if you can apply that same process to find f of 4. So as I set this up, do I need to adjust the bounds? Or is it already in order? It's already good, right? There's no need to adjust the bounds. It's already from smaller to larger, so we can just go ahead and plug in what we see. The regions from negative 2 to 4 are all negatives, so we can just say negative 6 minus 8. Okay, now I want to show you a second variation here. Second variation, the exact same steps. It's just that the difference here is there's actually an explicit definition for g of x. So what I want to show you is that if there's an explicit definition for g of x, there's no need to include an initial position. You just follow the rule, whatever it is, then that's the location. But if there is not an explicit definition of f of x, then you have to rely on initial plus displacement to get to the final position. Okay. So same diagram, same area, same regions. But now, because there's an explicit definition, I'm just going to replace negative 3 in for x and then just read the graph. Okay, before I read the graph, what could be helpful to be done? Yeah, let's read. It's just easier, feels more straightforward if we can just always read from left to right and not have to flip the signs of the numbers that we see in front of us. So pull a negative out. Change the order of your bounds. And now I can comfortably read from -3 to 1. So -3 to 1, that's just 7 minus 6. But then you've adjusted with a negative outside. Okay, try part B. Okay, we got a little bit of time. See if you can go to page 17. That's the start of your homework. We know we have to involve area for that diagram on page 17. So see if you can start finding areas of all those geometric shapes up top. Okay, page 17. Semicircle, triangle, triangle. We're going to have to find G of 2, which will involve the area. Okay, so. Radius is 2. Okay, so the function f is continuous on the closed interval from -2 to 7, consists of 3 line segments and a semicircle. The function g is defined as the definite integral from -2 to x squared of f of t dt. Find g of 2. We already have g of x, so we can just go ahead and make that insertion. -2 to 4, so that's the region of the semicircle and the triangle. They're both above the x-axis, so we can keep them both as positive. Next up, find g prime of 2. But before we find g prime of 2, we first have to find g prime of x. So we know there's going to be some canceling out here, right? Derivative of a definite integral here. Okay, so second theorem says we know these two operations cancel each other out. This f of t is not going to change much, but we do have to involve that upper bound. So that upper bound gets inserted in for t, but we also need to multiply by what? By the derivative of x squared, which is 2x, yeah. So the second theorem here, right? Derivative of definite integral will just result in just that f of x untouched, but the upper bound gets inserted in, and we also multiply by p prime, by the upper bound's derivative. Okay, so now I can replace every x with 2 and find g prime of 2. Go to your table here. What's f of 4? 0, right? Okay. Okay, so if I want to find g double prime of x, sorry, g double prime of 2, I need to find g double prime of x. To find g double prime of x, look at how this is set up. Can you tell what's involved here if I want to find the derivative of this? Product and, good, product and chain. Okay, let's get that set up. Outside's derivative times inside's derivative, f prime of x squared times 2x. Sorry, f prime of x squared times 2x. G, f, and back to g prime. Guys, I finished this up. I won't check this until Monday. Encourage you guys to study for your quiz. Work through the morning review. Video and key for the morning review is on the website. I'll send out a reminder. Bring your calculator. Okay.